In the span of his time at the Open University, he has also written more than 40 books. One of the most renowned and spectacular books used by many graduate students throughout the world is Thinking Mathematically, which he co-authored with Yoni Burton and Kay Stacey. This classic is currently translated into 5 languages, and it is one of the books that every student of problem solving never fails to get into. At the Open University, he led the Center for Mathematics Education in various capacities during his tenure there. He also produced the influential Roots of Algebra and numerous collections of books which many of us have access to while he was at the Open University. Currently, John is an emeritus professor of the Open University and a senior research fellow at the Oxford University, where he spends most of his time, according to Anne Watson, his wife, enjoying the sunshine when there is one something and mulling over his thoughts. Lately, in one of his books, which is a practitioner research using the discipline of noticing, John has managed to pen his lifelong collection of techniques and frameworks for informing the teaching of mathematics. Now, ladies and gentlemen, I'm certain that John will share with us some of his wisdom and thoughts that would engage us in fruitful thinking about what we have been doing for teachers and mathematics education, and spur us to think deeper into what we would like to do in the next couple of years. With this, would you kindly join me now in welcoming Professor John Mason to deliver his address. Thank you.
Thank you much for all of that. I think the honour is entirely mine to be invited to come to Phuket and to work with you all. And so I want to thank the organisers for inviting me. The outline of what I'm proposing to offer you this morning is as follows. Part of the throat clearing is that you are going to need some paper and writing, pen or pencil, because I treat you as participants who sit and listen, but rather as participants who participate. So I'm going to invite you to do some mathematical thinking, and I will explain why in just a minute. So I'm going to invite you, after the throat clearing, I will invite you to encounter some phenomena. I will invite you to notice how we use ourselves, how we use our powers, what it is like, what the lived experience is like of thinking mathematically. Of course, in a session like this, we can only have a little taste. Let me stop for a moment and check. At the back, can people hear? Yes? It's a stupid question, because if you can't hear, you wouldn't reply. Oh well, there it is. And we'll have opportunities, at least for me, to apply this to working with learners. Apply what you notice to thinking about how to work with learners. And particularly, I want to consider what I call the phenomenal conjecture, because I like playing with English language. Every mathematical topic in school and early university, this is a conjecture, every topic in school and early university can be introduced through some phenomenon which provokes students in a desire to explain, and or which can be, the topic can be reviewed by using it to explain some phenomenon. And what I'm hoping to do this morning is somewhat complicated. Namely, two ideas that I'm trying to put together. The first one is that phenomenal conjecture, which I've just outlined there. The other one is my concern about the rapid development of people presenting mathematics on electronic screens. I spent 40 years at the Open University. I know a little bit about learning at a distance. And one of the things I know is that students don't know how to learn mathematics. It really, really helps if they have interaction, physical interaction with a tutor or a teacher at some point who can show them how to go about learning mathematics. I'll say that again in a minute, but anyway, here we go. So ways of working. Everything that is said in this room, certainly if it's said by me, but everything that is said in this room is a conjecture. It is uttered so that it can be thought about and modified. George Polya, who was a major influence on me, spoke about getting the conjecture outside of yourself so that you can look at it. For me, that's one of the main roles for discussion in mathematics. There's an opportunity to work up something for yourself in the context of what is provided by me today. So I'm confident that each of you have come to this conference with a number of things that you are working on or want to work on, and that will be happening in this session. I've announced some of the things that I'm working on, and I will be more specific as we get going. You can take an opportunity to listen to others is important as a way of working, and what you get from this session will be mostly what you notice happening inside you as you attempt to deal with what I say. But let me remind you, everything that I say is a conjecture, and it must be tested in your own experience. Don't believe anything I say. It's dangerous. What the sorts of things you might notice, how you use your mathematical powers, how you might inform your future teaching. Now, this is where I go back to the e-screens business. There's an increasing use of e-screens for teaching and for learning from, whatever that means. Some people call it e-learning. I have a lot of question marks about that. But there are at least two directions that I've noticed. One of them is what you might call e-exposition. The internet is beautiful for presenting things, for telling people things. It's really hard for getting people to think about things. And the reason for that is the click and go phenomenon. As soon as you have your brain goes a little bit frozen or not sure what's on the screen, you look for something else to click, and away you go. And another direction is beginning to develop, which I might call e-enaction, where people are trying to use electronic screens to do what Brunner referred to as enactive representations, where you use the objects on the screen to manipulate, and somehow that's supposed to do what apparatus also does for you. And there are Angry Birds and the subject embodied mathematics. If you Google that, you get a number of different items. Now, for me, school, and I mean by that face-to-face school, could be about accessing scientific knowledge. That's what Vygotsky, that's how Vygotsky saw things. And it could be about formalizing the informal. In other words, formalizing experience that children already have and engaging in what the Dutch would call vertical mathematization. But in order to do that, often what we have to do is to informalize the formal in order to make it accessible. And John Dewey, oh, sorry, that came in the wrong place, but there it is. For me, my current has led me to the conjecture that with e-screens being ubiquitous, it is even more important that students encounter a teacher, show them how to learn mathematics effectively, how to internalize effective strategies. And a lot of what's in the middle here, if not all of it, is really what Dewey meant, I don't know what the 65 is, Dewey meant by psychologizing the subject matter. Right, just a little bit more throat clearing. The question really, the deep question, is when and how does vertical mathematization take place? The formalizing of the informal, the becoming accessible. How does it actually happen? And some people talk about abstraction by trying to make the abstract seem to be concrete, and the word reification is often used. There's a staircase theory of ascending levels, that people that to learn mathematics, walking up a staircase, and at each level you're a bit better at doing mathematics. I find that a really peculiar assumption, but it's only been around for 3,000 years or so, so it hasn't, we've had a fair amount of experience of it, and it seems to me it doesn't actually work. And there are spiral theories, such as Bruner's, of recount and reintegrating. Okay, I have an apology to make, and that is that I'm not going to work through the paper because, for several reasons. One of them is because I like to work on the edge, and having worked on the paper, I thought about those problems for quite a lot. So I'm going to offer you some other problems. But the first one isn't, just to get us started. So, that was a lot of throat clearing for me to indicate that there's a deep basis for the kinds of thinking that I'm inviting you to engage in. So, here's a task.
Jangan nantinya dulu kan.
Would you please turn to someone beside you and say what you saw? Do that now, please. There's no one beside you, turn around. Find somebody to say what you saw, please. The upper left-hand corner at the moment isn't very interesting. It just says 1. What I've also done for myself, I hope, is to turn the film into slides. Well, I've only got the first 50. The film comes off the internet, and as far as I can tell, it keeps going as long as you leave it there. I've had it run up into the thousands. But now I want to do it a little bit more slowly. Can you remember from what you saw, can you now predict what's going to come next? Mathematicians on the whole don't pay attention to color unless they're doing very complicated symmetry groups, so I'm not going to worry about the colors today. I haven't worked them out, that's basically why. And I'm going to now run through the slides for a little while, but I want to pause for a minute. One of the things that could be worth paying attention to this morning are the pedagogic strategies that I try to give you a glimpse of. So for example, we've already had say what you see or say what you saw as a pedagogic strategy, which I think is vital if you're going to try to learn from the internet, off an e-screen of some sort. To stop every so often and say, hang on, what was it that I saw happening? I'm willing to bet that lots and lots of kids don't do that when they're using the screen. Okay, and then another one is to predict what's coming. So can you remember what comes next?
Triangle.
Okay, I'm going to show you a sequence of them, and then I'm going to stop and ask you to predict what comes next.
Square.
Oh, I should mention, all of the slides will be on my website when I get home, including applets that go with the tasks in the paper that I'm not going to use this morning. Let's pause there. Turn to a neighbor and give them a story for why it looks like that. Why does it look like that?
Because
Very, very easy to end up with students trying to catch up with the teacher rather than trying to anticipate or predict. So I'm trying to push you into experience of what it's like to predict. It doesn't matter if your conjecture isn't quite right, if your conjecture needs modifying, because then you'll learn something. If your conjectures are always right, then you're not going to learn very much. Okay, here's 10. Does that feel good? You got it. You predicted it. It feels good. People talk about motivation for mathematics. Having a sense of accomplishment because I predicted what is coming is so much better than a sense of accomplishment because I've managed to reproduce what the teacher told me last week. Shall we move on a few? 11. 12. Do a quick sketch of what 12 should look like, please. Pay attention to how you are thinking about it. How do you know that 12 is likely to look like that?
Nadi-divide siya into prime factors. Yung, diba?
Yeah. That's by 3, no? To make it 4.
So yung per set ng, kunyari, 12 into prime
When
factors.
I first saw this film, I thought it was beautiful. Anybody agree with me? I thought the film was beautiful. And then I started to think about how would I use it. And so one of the reasons I wanted to use it here is to work on with my conjectures on how it might be used. Because it seems to me that simply showing the film is simply showing a film. But it's what you do with it. Or to put it another way, the notion of tasks being rich. We're looking for rich tasks to use with our students. I'm of the opinion, remember, everything I say is a conjecture. I'm of the opinion that it's not so much the task that is rich, but whether the task is used richly. It's how you use the task that really matters, I conjecture. And so I'm exploring with you some of the ways that you might go about using a simple film like this. Also, I'm trying to offer something that could be used at primary, as well as anywhere in primary, as well as at secondary. Do you want to see a few more? I'm getting 3 or 4 yeses and a lot of no information at all. I'll go with the yeses. Okay, let's move along a bit. 13.
Prime.
14, are you anticipating?
7 times 2.
You've got a sense of how it's going to work now. 14. One of the things I notice about watching the film is that after about 35, people start to be bored. They start to, but I'm not sure that they're bored for the right reason. I'm not sure they're bored because they know what's coming, or simply that something is coming. 15. How about 16?
Square.
2 times, or 8 times 2.
4 times 4.
Pwede rin tag 2.
16. 16.
Or 4
The one
na.
after 15.
Ano, 4, 4.
4, 4, 4.
On the whole, the slides come in order.
4, 4, 4, 4. Oo nga, 4. Ay,
I'll
maraming
randomize them for next time.
nakapabilog siya ng...
16.
Oh, di ba? Tama, 4, 4, 4. Oh, di ba?
Okay, I'm going to push along now. I'm going to run up to push along a bit. There's 25. What about 28?
4 and 7.
I'll get you ready. There's 26. There's 27. What about 28? What's it going to look like?
That's oh, diba? 4.
Conjecture needs modifying, perhaps. That's okay. That's good. That's good. Okay. One of my claims, which I will try to, I hope I will get to in the end, is that one of the things we do not seem to learn from experience. Footnote, everybody thinks that experience is good, especially in the mathematics classroom. I want to experience mathematical thinking. But one thing we don't seem to learn from experience is that we don't often learn from experience alone. It takes more than simple experience in order to learn something. And the only other thing that I can think about that is helpful is reflection. So I want to invite you now to spend about 5 seconds asking yourself whether it would be appropriate in some lesson that you teach to use a strategy like say what you see, or how do you know, or can you predict? Those are 3 that I can think of. There's at least there's a 4th one, but I haven't mentioned it explicitly. So 5 seconds, just imagining yourself into the future, in some situation, using one of those. You probably already do, but reinforce yourself, imagining yourself doing that, please. Existence theorem that I own a jackal. Right. An arbalos is a shoemaker's knife. It's the part of it which is green, so it's this part. And there are a couple of questions about it. First of all, would you turn to somebody and say what you see? Or indeed, what you saw? What did you see? Draw a quick sketch. Say it to somebody else, please. Part of the vital move, I think, that's one of my conjectures. It's a vital move for students to have internalized so that they do it naturally. So that they're telling themselves a story, they're constructing a narrative as they're working on a stream. A couple of questions before we get going with this one. Well, here's a fact. Things that look like semicircles are semicircles. Is that okay? But this is what goes on in mathematics. This is what mathematics offers every single child. In the upper primary, lower secondary area, is an epistemological shift. A shift from something's true because it looks right to something's true because I can justify it. You can't tell whether those are semicircles, they just look like semicircles. I have to tell you that they're semicircles if we're going to make any progress. Once I've told you that there are semicircles, then we can start asking questions. But mathematics is a wonderful domain for helping students to make the shift. There are things they can know because they must be the case, and not things that they know simply because some adult has told them and they're supposed to memorize it or otherwise internalize it. So, question, what is the perimeter of the arbalos?
Yes.
What is the perimeter? Well, there's a lot of things you don't know, and some book that I came across a while back asks, what do you know and what do you want? it suggests those are useful questions. They came from George Polya and from my teacher in high school, who taught me always to begin with given, to prove, and then start writing down the proof. We turned it into what do you know and what do you want as good questions. So what do you know? You know they're semicircles. That's about all you know. And what do you want? You want the perimeter. I hope you've drawn a sketch, because one of the things you want to do mathematically, a major mathematical move, is to introduce what is only present implicitly rather than explicitly. I hope I'm not boring you by taking by spending so much time working on basics.
So, pinari may A, B, C ka.
Fundamental.
Yeah.
Diba?
So,
A to C.
I need some notation and I need to denote things that I know, namely
by
these
rare
are semicircles. So I offer that.
It's 2 pi rare.
And now can you tell me what is the perimeter of the arbolas?
Ah, diba?
Sorry. You're given little r, big R.
R minus R. So yung radius, diba? Kukunin mo yung circumference na. So you're given
I want to
2
give
pi
you
R,
a
diba?
chance to think about
Yeah,
it.
2 pi rare.
2 pi R. So 2 pi R, big R. Plus, half lang nun, half lang. 1/2 2 pi R, big R. Plus
So
1/2.
that's pi rare?
So just pi R.
Yeah.
Now so far what I've offered you is a
By
static
small r.
picture.
Okay.
There's another way of
By
introducing
R
it,
minus R.
which I'll show you in a minute, which is as a dynamic. But I wanted to give you a chance to work on what is the perimeter. I hope what you found is it's the perimeter of the big semicircle, but as a whole circle.
Yeah.
It doesn't actually matter what little r is. So now you're anticipating what an animation might show, namely an invariance when little r changes. But hello. Oh, don't tell me. Come on. I'm trying to be helpful. When I put up a response like that, I destroy something for you because I may be breaking into your thinking, but I need to make some progress this morning through various tasks in order to give you a variety of experience. There's another question around, seems to be fairly obvious, which this machine doesn't want to do. Namely, what is the area of the arbolas? And I'm going to leave that for a moment. You can be thinking about it while I set up the two little circles. Turn to a neighbor and tell them what you think you saw. I'll run it once more. Here. Another mysterious item, and that's the film. Oh yeah, it's a bit more. Sorry. Now let me remind you that according to this calculation of the perimeter of the green region has been invariant throughout the changing. No matter where this point down here, no matter where this point here, it moves, the area of the green stays invariant because it's independent of the little r. It depends only on the radius of the big one. So what I'm trying to do here is to indicate that using some sort of animated phenomenon, preferably one that actually is compatible between your system and the projection system, so you don't run into my troubles. Using some sort of an animation, it has the potential for raising questions about why something happens. But before you deal with why something happens, you've got to agree on what it is that's happening. So just to give you a little taste of that, would you please turn to a neighbor and say what you think is going on here. Say what you see is going on in that picture there. Could you do that please now? That various bits of language like tangent, possibly, might have come up in the vocabulary. But one of the things you may have noticed is it's actually quite difficult to say to somebody what you're seeing happening in a diagram. It is actually not trivial. And that's why we really need to rehearse this over and over and over so that students internalize it into their own thinking. Okay, here's a task which can be used in middle primary up until lower secondary, depending on the competence of your students. Let's see if I can change slides. Doesn't seem to be the case. Okay, something's gone wrong here. Hello? Okay. Would you please write down 4 numbers in a 2x2 grid? Would you please write down 4 numbers in a 2x2 grid? Anybody who wants to use root 2 plus root 3 divided by pi is perfectly welcome to, but I recommend against it. I recommend you use a whole number, just to start with.
Wag the whole number. Square root of 3.
I'm going to ask you to do some things to your grid. So I'm going to show you my grid, but I'm hoping you've got a different one.
7 pi.
That's my grid, but I'm hoping your grid is different. Okay, now we'll do some calculations. Would you please add together the products along the rows? So that's 8 times 5 plus 2 times 3.
46.
And I get 46. But if you do that to your grid, please. On the right-hand side of your grid, would you please subtract the bottom right from the upper left? Bottom right from the upper left. Okay, now would you add together the products down the columns? That's 8 times 2 and 5 times 3, or whatever it is for yours. And in my case, I get 16 plus 15, which is 31.
Come on, come on.
And would you please subtract the bottom left from the upper right? The bottom left from the upper right to give you 5 minus 2 equals 3. I bet you're wondering what on earth this is about. Would you now please subtract the column product sum from the row product sum? So 31 from 46. And the answer is, in my case, 15. And would you please multiply the results on this side, and 3 times 5 is 15. My conjecture is that you got different answers, but they're the same. And since they're the same, and since, am I right? Is my conjecture valid? Did you get the same answer? Really? There must be something going on. This is an example in mathematics where you have lots, you can use students to have a distributed examples. So everybody's got a different example, but there's a phenomenon going on. There's something that's invariant. I put it to you that mathematics can be seen, certainly, yeah, I'm going to say generally, mathematics can be seen as the study of invariance. What changes, what's allowed to change, but what must remain invariant. That was going on with the Arbolas as well. In fact, it was also going on with the film, but you have to be a little bit abstract about what's invariant and what's the same. So when you see the sameness, and everybody seems to have
the same, you smile. Everybody smile?
Did you try that?
So now we have a question.
So, same.
What I'm
It's like-
actually trying to do here is to show how a very simple arithmetic fact can be turned into a phenomenon to try to motivate students to find out why did everybody get the same answers left and right. Now everybody who's familiar with algebra can quickly throw letters in, but one of the ways you're working with this task is to introduce the notion of algebra, but that's not my remit here, and so I'm not going to. But this task is one of many, many that can be used to introduce students to the notion of working with as yet unknowns. Let's try it again.
Same pa rin ito. Cool.
Turn to a neighbor, please, and say what you saw happening. So I've been trying to give you some examples of pedagogic strategies which I think are vital for learning in any context, and particularly from learning from the internet when you're on your own. I want to just show you a couple more phenomena to try and justify my conjecture about the use of phenomena to provoke almost any or probably any topic in school mathematics. I'm well aware that there's a cultural propensity in East Asia to beautifully wrap any object that someone is going to give to someone else. And of course, when you wrap things, there are a couple of ways of putting a ribbon on a box. For example, you can put the ribbon over one corner, under the other two, and then up over the third corner. So the dotted ones indicate that it's gone behind, and what you see when you look from the top is just two diagonals on the corners. Is that familiar? It's not very common, but I like it. Of course, there's another way of doing it, but there's a question. Where does the ribbon have to be in order to be tight? Where does the ribbon have to be? Can it be right across the middle, or does it have to be close to the ends, to the corners? In other words, where must these things be in order for it to be tight? And of course, there's the ordinary way of doing boxes, across one side and then along the length, and it looks like a cross from above. And then we have a question: which one uses more ribbon? That to me is a phenomenon which comes about when I observe people in shops wrapping things up. And at Christmas time, when I'm trying to wrap things, and I get my thumbs all over everything, and I ask myself, how long is the ribbon? Which is the best one for using with the ribbon? Another phenomenon which I just happened to notice while I was being introduced this morning. If you have a look at the central projector, look at the angle of the top of the projector. Now look at the position at the top of the screen. Presumably the top and the bottom of the projector are parallel. Let's take that as an assumption. The bottom of the projector is aimed more or less at the bottom of the screen. The top of the projector is certainly not aimed at the top of the screen. What can I deduce about what's going on inside the projector? Seems to me that there are phenomena all over the place which bring up questions. This one being a question about angles, the box ribbon. Given the way things are working, I'm not going to show you how to resolve it. I'm hoping this will work, but I'm fearful it's not going to. This is an example which I really like, and it's aimed at sort of upper secondary, really. Each row and column is an arithmetic progression. I give you that. What number appears in the upper right-hand corner, where in the pink square, the pink cell? Turn to a neighbor, see if you can work it out between you. What number appears in the upper right-hand corner, the pink cell up here? All I'm going to tell you is that each row and each column is an arithmetic progression. I didn't say they're the same arithmetic progression. And I'm willing to bet that each of you find students in your own class who have exactly that response to tasks. But I'm going to now convert this into a phenomenon. I hope. There it is filled out, and 127 is what the computer thinks it is, so that conjecture is justified. But what Sundaram came up with was the following.
And then yung plus 1, plus
a number appears. A number appears in this grid if and only if one more than double it is composite number, is not prime. One more than double it is not prime. I'm hoping that your immediate reaction is to test that conjecture. My eye goes to number 40, so let me test it on 40. I double 40, I get 80. I add 1, I get 81. It's not prime. The conjecture is justified, or validated, I mean. Try another one. There's something I can do mentally, easily. 22, double it, add 1,
43.
It's composite. Now the applet has little buttons down here so that you can actually slide this as a window, and you can go quite far, not arbitrarily far obviously, otherwise the numbers would get too big, but you can go quite far to the right and up. You can also go to the left and down. So you can get a snapshot or a window on this effectively infinite grid. But the question, I'm hoping that at least some people are finding it a little bit surprising that you can have a statement like this which says that a number is not prime. That requires some mathematical sophistication to appreciate, but once, as an appreciation, now there's an issue about how on earth will you justify this? Okay, I think it's time for me to, I'd like to show you quickly this one, if it's going to work. Let's just see if it works.
Snake.
I'm presuming you've made some predictions now, so I'm going to try and push it along. There we go.
Square. Yeah.
Now I'm going to pay attention to the square numbers. Where are the square numbers? That's got to suggest a conjecture. Isn't that a little bit surprising? The square numbers appear like that. So there's something to justify. But there's one of the things that I think the e-screens are very bad at least currently, or the way people use them currently, is to provoke students into saying, well, I want to justify this, but is this all that's the case? How can I modify, what can I do to change something and see whether it's still the same? I still have the same phenomenon. So I'm going to invite you to assume for the moment that the square numbers will always appear on diagonals, and show you this one. Here I've got some blocks. The pink ones are blocks. I'm not allowed to put numbers in there. Hello? There we go. And it's going to pick out the square numbers as it comes to them. Are you predicting predicting. Oh, well, that's in a funny place. Oh, looks like we've broken that one. Let's see if I can push it along a bit. Turns out that 49 is there, 64 is there. Oh, I'm starting to get some alignment. And if you carry it on, in fact, you get an alignment. Now, my question, so here again I've got a phenomenon taking place, namely the square numbers appearing on diagonals as you make a spiral. But it looks as if it might even be the case that when you put obstacles in the way, as long as you keep them in the center and don't have them going on infinitely far, if you put in a finite set of obstacles, then eventually it looks as if it may be the case that you still get the same phenomenon, that eventually the square numbers appear on two straight lines. Now this happens to have a justification for this can be related to deep features about the topology of the plane. But there's something which high school students are perfectly able to explore for themselves simply by using their elementary algebra. Okay, I have other examples, but I'm now going to run through, see if I can persuade this to work. No? Okay. So, I have some questions for you. What is it that engages attention for students? Anybody got students who don't really pay attention? I think most people have a few at least. What is it that engages attention? Well, it seems to me that mathematical storytelling is one of them. Getting people to give a narrative about what they see happening is one way to engage people's attention. In some of the papers that we're going to be experiencing this week, we'll find many others. Placing things in a meaningful context is one that's very popular at the moment. Yeah, okay, I haven't got time to say more about that. Getting learners to make their own questions. I've already seen in the proceedings a picture from 1924 of Chinese students being invited to formulate their own, Chinese or Japanese, I can't remember which now, to formulate their own questions, and then these are put up on slates in the classroom. That's a practice which has died out, and we're having to rediscover it as an important strategy. But it's something that we also want people to do for themselves when they're working on e-streams, asking their own questions, because that changes your relationship with the question and increases your motivation and your interest in participating. Surprise is an obvious one. I've tried to provoke you into surprise a couple of times this morning. I'm hoping that you've got some things left over from what I've been doing where you're wondering if it really is true, because I've asked you not to believe anything I say. A desire to explain or make sense of some phenomenon, whether it's the angle of the projector or whether it's something on an e-stream. But also, it's important for engagement and motivation that the students trust that the tasks they're given are actually doable. There's a trust relationship that's necessary between the teacher and the student. The students have to trust the teacher. It helps to be developing a positive disposition and developing self-confidence that comes through success, but not success in completing a lot of exercises, success of the kind that I hope you experienced when you were predicting in the film, and you were able to predict mostly or entirely what was going to come on the next screen. And that all requires a supportive environment, a conjecturing atmosphere. I've just seen this. Tasks to students to do, and there's a didactic contract which is going on when we do that. I reckon that tasks are meant to produce activity, hopefully mathematical, and that mathematical activity is supposed to produce experience. But the question is, one thing we don't seem to learn from experience is that we don't often learn from experience alone. So we have questions like, what provoked activities? At least many of you engaged with at least one of my tasks. What actually provoked you into activity? Just have a little think about that. What provoked you into activity? That's a useful question to get students to ask themselves over and over again. What was effective in what I did? What powers did I use? What mathematical themes did I encounter? What could I vary and still use the same ideas? And finally, I want to bring to your attention the question, what is it that makes a phenomenon actually a phenomenon? What makes something like, for example, the projector situation, what makes it into a phenomenon? Well, I reckon that a lesson without an opportunity for students to generalize mathematically, a lesson without such an opportunity is not a mathematics lesson. What turns an incident into a phenomenon is the act of seeing through the particular to a generality. Now that is something that what I've seen on the internet, on e-screens, I have not encountered very many situations where that is really being provoked. It's provoked in me, but I've been trained to do that. One of the roles of children in school, and teachers in school, has got to be to get kids to internalize for themselves this desire to see through the particularity to a generality in order to be aware of phenomena rather than of everything they encounter as being special in some way. And finally, any follow-up, if you want these slides and the applets, which they do actually work, but not when you're using an RGB projector, it appears, then you can get those on my website, which is up there. There's various other things which might be might be helpful if you wanted to follow up some of these ideas. If you would be so kind as to spend 5 seconds now asking yourself, is there something that you experienced this morning that you would like to remember to make use of in your own situation? Could you please imagine yourself in that situation using it? Do that now, please. Conferences like this is that in every session I come across something, at least one thing, often 2 or 3 things, that I think, gosh, I'd like to do that. Gosh, I'd like to remember that. Sometimes I even make a note in my little notebook. And then I get home, I've got so many other things to deal with, I don't even get to look at the notebook. I've got hundreds of notebooks piled up in my office, full of lots of good ideas. May I make a conjecture? If before the session ends, you imagine yourself at your place of work, actually trying something out, there's a much greater chance that you will actually succeed in trying that out. Thank you very much for your attention.